Hi, my name's Chris Pennell. I'm a cancer researcher here at the Masonic Cancer Center. We have one of only 49 comprehensive cancer centers in the country, so it's an elite organization. I don't know why they let me in, but they did, so I snuck in the door. So what I wanted to do is to give you just a brief overview of cancer and then who does what in cancer research, and then wind up with why I think you should go into cancer research. So one of the common misconceptions about cancer is that there's going to be a cure, one cure for cancer. The reason that this is a misconception is that cancer is not a single disease. Cancer is an umbrella term that describes over 210 different diseases because that's how many different types of cells we have in our body. So each of these geometric symbols represents a different tissue, lung, liver, kidney, and so on. So this white pentagram represents blood cancers or leukemias or liquid tumors that we call them. And so these would be cancers of your white blood cells. Those different color pentagrams represent different white blood cell types, so T cells, B cells, myeloid cells. Each one of those can become malignant. Then if you look at the red one, myeloid cells, there's chronic myeloid leukemia, acute lymphocytic leukemia. There's a whole bunch of different types of diseases even within that one. And then if you look in an individual patient who has a disease, most oftentimes that disease arose from one rogue cell that decided not to obey the rules. And that cell will replicate and replicate into billions and billions of cells. That replication process is not 100% the fidelity is not 100%, so mistakes are made. So even within one tumor, there are differences. This is why cancer is so difficult to treat, because it's not a single disease, and even in a single person, there are slight variations of diseases within that person. Cancer affects all of us, either directly or indirectly. 1 out of every 2 men and 1 out of every 3 women in the United States will develop cancer in his or her life. That's 40% of the population. So if you don't develop cancer, somebody you know and love will, which is why we're interested in trying to figure out how to treat it. So I titled my talk Cancer Medicine in 2020 and Beyond. I think I was inspired by Toy Story. But anyway, the way that the field is going in a direction, it's going in a direction called precision medicine or targeted therapy. And what this means is that through genetics and pharmacogenetics and immunology, we're able to identify a particular Achilles heel in each tumor and attack that with a particular drug that's going to work in a particular patient. So rather than having a carpet bombing approach, which is what chemotherapy is essentially, we're going to have targeted approaches. And so the treatments are tailored to not only the genetic lesions in that tumor that allowed that original cell to become malignant, but your own biochemistry, how you deal with drugs. And so many tumors, even though they may be from different tissues, share commonalities, common pathways that have gone awry. And there are drugs that can target those pathways. P53 is a common mutated protein in a variety of malignancies. There are drugs that can target that. So if you have a P53 mutation, you're going to be treated with a particular drug because we know that there's a high likelihood that that drug will attack that pathway. But if you've got 4 individuals with the same type of tumor, let's say they all have B-cell acute lymphocytic leukemia, and let's say we have 4 different drugs that can treat that disease, well, how do you know which of those drugs to use? I may be able to tolerate drug A, but not B, C, and D. They may be toxic to me. So what we're doing is sequencing the person's own healthy DNA and trying to understand how their enzymes will react with these drugs such that we can give the right drug to the right person for the right disease. This is the way the field is going. The big bottleneck in the field, if I were starting off at your age, I would get into bioinformatics. We're really, really good at generating the data. It's not that easy to analyze the data and make sense of the data. And so I have to talk to bioinformaticians, I can't even say the name, statisticians, computer scientists, to analyze literally hundreds of thousands of bits of data to try to come up with a comprehensive story out of it. I understand the biology, but trying to make sense of all of those data points is where the bottleneck in the field is right now. So who does what in cancer research? There are 3 types of cancer research: basic, translational, and clinical, and each asks a fundamentally different question. Basic research asks, how does it work? How did that cell become malignant? What went wrong? Translational research asks, okay, now we know what went wrong. How can we use that knowledge to come up with a therapy to treat this disease? So you're translating basic knowledge to applied knowledge. And then clinical is, how does this new treatment compare to the current gold standard of treatment in the field? So let's say Sean is a cancer researcher. He saw the light early and didn't go into neurorobotics, but he realized that cancer was the way to go. And he develops this novel therapy that he thinks is fantastic, and he's worked for 20 years on it, right? Now he wants to get that out into the clinic where it can help people. Well, for every disease, there's a current gold standard of treatment. It may not be very good, but it's the best that we have. So if Sean says, mine is going to be better than that, he has to prove it in a head-to-head trial. And that's clinical research, clinical trials in cancer research. And if Sean's new therapy is better than the old current standard, it becomes the new gold standard, and it's used in patients. So this directionality is called bench-to-bedside research, where you're going from the laboratory bench to the hospital bed. It also can go in the other direction, and this is the direction my research is going now. There's a novel immunotherapy that has been a life-saving, game-changing therapy for patients with liquid tumors. There have been some unanticipated fatal side effects. People didn't anticipate it, no idea how it happens. So we've developed a mouse model that captures both the good and the bad of this immunotherapy. It causes the neurotoxicity. It causes this systemic inflammation in the mice. And the mice, look like people in response to this therapy. So now, using the power of mouse genetics, we can try to understand the underlying problems and then develop a better therapy. So it's a back and forth iterative process. So with these three types of research, who does what? If you get a PhD, which is a doctor of philosophy, you mainly are interested in at least in cancer research, about mechanism. How does it work? What's the underlying biology? What's really going on? If that's what gets you up in the morning and that's what drives you, you probably want to get a PhD. If you're more interested in taking care of people, you'd want to go to medical school. But as you can see, there's significant overlap between the two. Although I have the PhD triangle stopping before patient care because they don't let me near people, just mice, okay? So there's a fine line there. But MDs can work with mice as well as people, right? But which of these two routes you want to take really depends upon your personality and what drives you. My wife is a pediatrician. I can read an article in Science, for example, about some novel drug that's going to work well for pediatric patients. I'm jazzed up about how it works. She doesn't care about that so much as to what's the clinical outcome. So it's a different way of looking at things. And then there's a whole host of individuals that span this spectrum with other degrees. You need at least a bachelor's degree because these are time-consuming, expensive procedures that you need a baseline knowledge for, so you can't do this right out of high school. You need at least a bachelor's degree. The more advanced the degree you get, the less people tell you what to do. So one of the reasons I wanted to get a PhD was to minimize the number of bosses I had, right? So as long as I do a good job and bring in money, people leave me alone and they let me do what I want to do, which is great. But everybody has a boss. So that's one reason to get a PhD. The other reason is that it allows you to really dig deep and delve deeply into a problem and then to choose what you want to do. So that's that. So how did I get here? The picture in the upper left is, I took it last night from my high school yearbook. It's in black and white because this was before color was invented. And so it goes way back. So I'm from Long Island. I've tried to attenuate my Long Island accent because I went to North Carolina, and at the time they weren't fond of Yankees. So I did that to survive. But I grew up on Long Island in New York. And I played soccer in high school. My dream job would have been to be a professional soccer player, but I was also a realist and knew that there was absolutely no chance of that happening. So science was not my plan B, but my realistic goal. I always loved science and did well in high school. Then I went to a school in upstate New York. I love hockey. I don't know, that's why I'm here. But anyway, so I went to upstate New York and went to college up there. And then between undergrad and grad school, I had a summer research job in Switzerland. It was the first time in my life I simultaneously had money and time. Usually one or two of those are limiting. But for this summer, based on what I was making before. I had a good amount of money and I had a lot of time, and it was just a wonderful experience. And this is, on the penultimate slide, one of the reasons why it's fun to get into science, because you can do things that make you have a lot of fun doing it, and they pay you to do it, right? So then I went to graduate school, University of North Carolina at Chapel Hill. My children grew up hating Duke University without even knowing what Duke University was. So the intense rivalry there is something that I didn't appreciate until I got there. And then kind of bounced up and down the East Coast before arriving here in the mid-90s to help a newly formed cancer immunotherapy group, which is what I've been doing ever since. And so you can read the rest. So why would you want to choose a career in science? You really get to figure out how nature works. So the way I think about it is that think of yourself being in a bubble. Everything inside the bubble is what humanity knows. Everything outside the bubble is what we don't know. Scientists push the bubble, right? And so I'm pushing it in one way. Rosemary's pushing it in another way. John and Sean are pushing it in a different way. So we're all pushing the bubble out. Artists do this as well. And what happens is the net result is that the bubble keeps getting bigger and bigger, and we incorporate more of what we don't know into what we do know. That's fantastic. I don't know. Anyway, that's great. Okay. You get paid to do your hobby. I'm getting paid to do what I like. It's, how can you beat that? I went to Paris last weekend for science, and then I visited some friends in Switzerland that I hadn't seen in a number of years, and they paid me to do it. How can you beat that? It's fantastic. And you get to meet great people worldwide. So I didn't have to, they put me up at their house, so I didn't have to pay for a hotel. You're constantly challenged, and you contribute positively to society. So I think all of these reasons are what drives almost all of us in science and engineering to get into the field. And so with that, I'll stop and take any questions. Yeah.
If someone's interested in immunotherapy, what path would you recommend to get into?
You need a strong background in genetics and biology. Obviously, you need to know something about the immune system. But people come into one field in a variety of different ways. So it's hard for me. I would almost argue that you need a strong basis in immunology and biology and genetics, okay, and that's the foundation. Other than that, you can come at it from a variety of different ways. And so I would really argue that you follow your passion and what really gets you excited. And then if you find a problem that you want to apply that to, you apply your unique skill set to it, and then you collaborate with other people that have skills that you don't have but you need to bring to bear on the problem. So I would not put on too restricted a set of blinders, particularly at your point in your career. But immunotherapy is fantastic. I mean, it's revolutionized the field of cancer therapy. Yes?
How can engineers contribute to developing treatments for cancer?
Well, a number of different ways. And so, for example, one of the hallmarks of cancer is metastasis or spread, and cells physically move along highways, cables in the body. If we understand the mechanisms of that, we can perhaps interrupt it and reduce or prevent metastases. So there's a fellow, Dave Odie, who's a mechanical engineer, he's got a large grant with a number of engineers as well as biologists trying to understand how cells move and how we can stop them from moving. So that's just one way.
Yeah, and I'll just say, as an engineer, we work with immunologists and biologists on immunotherapy. And also, the medical device industry here has hundreds of companies that make local devices that treat cancer. And I'd be happy to chat with you if you want about that.
But yeah, the buzzword is team science. So these issues are so complex that no one individual has all of the tools necessary to address all of the problems. So you've got to collaborate, right? And the good thing is that you get really excited about it. So I told John I could go on for 3 hours, so he's going to cut me off. But so with our mouse model, one of the problems is neurotoxicity with these immunotherapeutic strategies. Totally we didn't anticipate it. So I've just submitted 2 or 3 grants with a couple of neuroscientists that I would never have talked to before I had this problem. They're excited because it's a new area for them. I'm excited, and so that's one of the advantages about working at a university like this, is that invariably there's somebody that can help you. The problem is finding them.
Fantastic. Well, let's thank our speakers.